Hello, everyone. We're going to get started on 4.6. Just a second. All right, 4.6 is about rational functions. And I think the best way for us to talk about these is really just to jump right in. So a rational function is basically a function where you have a polynomial divided by another polynomial. And we defined polynomials in the previous parts of chapter 4. But basically, polynomials don't have negative exponents. They just are a list of terms, and the exponents help you define the degree of the polynomial. We're going to call this function f of x, and it's defined by p of x over q of x, where q of x and p of x are both polynomials. And we know that anytime you have a fraction, you can never have a zero in the denominator. So q of x could never, ever, ever equal 0. So that would be when it says state the domain, that is what it means by that. This is a rational function because it has a polynomial over another polynomial. But this polynomial could never equal 0. So we have to say could not equal 0, and we solve for that. So by adding 1 to both sides, we get 3x's cannot equal 1, which means that x cannot be 1/3. So that is going to be the restriction in our domain. So this is a rational function. And x cannot equal -3. So the domain is all of x such that x cannot equal 1/3. I said -3, but I meant 1/3. Okay. So again, it's a rational function because you have a polynomial and another polynomial. Now, when we talk about what the domain is, we have to say the domain cannot ever the denominator cannot ever equal 0. So you solve to find that. In B, is B a rational function? It looks like it's just a polynomial, but there may be something we can look at. There it is. Just like any whole number, you can write it as a fraction by putting it over 1. You can take any polynomial and put that over 1. And then it again is a rational function. And since q of x is equal to 1, 1 will never actually equal 0. How can 1 equal 0? It can't. So therefore, the domain is all real numbers, because you would never have a 0 in the denominator. C. C is not a rational function because in order for it to be a polynomial, you can't have any square roots. So it is not a rational function. If you were to find the domain, then you would say take the denominator and set it equal to 0. Well, this is a quadratic, so we know that there's going to be 2 numbers that make this equal to 0. So the first thing is we can factor out an x from the first one and factor an x from the second one and say that x cannot equal 0 and x minus 2 cannot equal 0. So that means x cannot equal 2 and x cannot equal 0. So if we were to write the domain, it'd be x is such that x is not equal to 0 and x is not equal to 2. Oh yeah, and x has to be greater than or equal to 0 for that square root symbol. Okay. D is not a polynomial either because we have that absolute value. Remember, a polynomial is just a list of normal terms with no absolute values, no square roots, no negative exponents, and all of that good stuff. X squared plus 4 is in the denominator, so we set that equal to 0, and we say which values make this equal to 0? -4. Well, there is no value that when you square it, you're going to get a -4. That just can't happen. It's going to be a complex root. So no real number would make the denominator equal to 0, because there is no real number that when you square, you equal a negative. So the domain is all real numbers. All right, so there's this real funny, weird word. Okay, first off, let's wrap up example one. Example one is all about just figuring out what is a rational function and finding out the domain. Remember, rational functions are where you have a polynomial over polynomial. And remember that the denominator can never equal 0. And you're going to use your different strategies in your toolkit to be able to figure out what would make that denominator 0. Now, moving on to the next topic, there's something called an asymptote. An asymptote is where it's like a line, a boundary line that you can't touch. So an asymptote in some ways can be seen as like an electric fence. If you can get really close to that electric fence, but you better not touch it. The way I remember that is asymptote, like don't touch my asymptote. Don't touch my asymptote. Okay, I just made that up. But anyway, an asymptote is basically a line that you cannot touch. The function might get really close to it, but it will never actually touch it or cross it. And so horizontal asymptotes look like this. And so they're going to be defined by the y value. So that's -1, -2, -3. Y equals -3 is the horizontal asymptote in that picture. For example 3, we're going to be looking at how do you find horizontal asymptotes when you don't have a graph. So you obviously could graph these and be able to say, oh, that's my horizontal asymptote by looking at the graph. If you don't have the graph, then you have to follow one of these 3 rules. So here are the 3 rules. If the degree is the same for the top polynomial and the bottom polynomial, then the horizontal asymptote is going to be the coefficients. If the degree in the top one is bigger than the bottom, so it's like top heavy, then there's no horizontal asymptotes. If the degree in the top is less than the bottom, so it's bottom heavy, then the horizontal asymptote is 0. So I would say make you a little chart to remember this. Okay, so degrees and then horizontal asymptote. And we identified that as HA. So if the degrees are the same, then you take the coefficients. If the top is bigger than the bottom, then there's none. If the top is less than the bottom, then it's 0. So in this case, we have the degree of 3 in the top and the bottom. So the horizontal asymptote is going to be 5/2. The coefficients of the degree, the leading coefficients, 5 and 2. On your test, it's just going to be just like this. It's going to give you a rational function. It's going to say, hey, what's the horizontal asymptote? So using that same chart, this is a 1 and this is a 2. So this is bottom heavy. Bottom heavy means the horizontal asymptote is 0. This next one is top heavy. So the horizontal asymptote is none. Top heavy, none. Bottom heavy, 0. Equal leading coefficients. You will have to memorize that. All right, so that's for horizontal asymptotes. You basically have this chart. For vertical asymptotes, which means a vertical line that it can't touch, x equals, you're going to basically be looking at the denominator. The values that make the denominator 0, remember you can't touch those, you cannot have those. Those are vertical asymptotes. So the vertical asymptotes usually can be found whenever you find a domain. because the domain, if there's restrictions in the domain, those are your vertical asymptotes. So find the vertical asymptotes for this function. Again, for vertical asymptotes, we just look at the bottom and we say, hey, where is this equal to 0? X cannot be -1. Therefore, my vertical asymptote is x equal 1. The line of x equal 1 is going to be a electric fence that you cannot touch. All right, so we're going to have some practice on example 5. Notice that when you have a rational function, it has to be written in the lowest terms before you can find the vertical asymptotes, because sometimes they can cancel each other out. So for example, we have this numerator that is x squared minus 1, but you can factor that, and that's going to be x minus 1, x plus 1. Remember that this is x times x, which is x squared, 1 times x, which is positive x, -1 times x, which is negative x, and then -1 times positive 1, which is -1. These two middle terms cancel, and you're left with x squared minus 1. So that's how this is equal to this. So if we write that as our function, then that can also just be written as x plus 1 times x minus 1. And when you have something in the top and the bottom in common, they actually cancel each other out, because like 8 over 8, that's 1. 2 over 2, that's 1. So x plus 1 over x plus 1, that's also 1. So anytime you multiply by 1, you don't have a value. So f of x equals x minus 1. That is what this is. So of course, then our denominator is just 1. Like, we don't have anything that could make our denominator 0. So our vertical asymptote none. All right, so example 6, this one we're going to be looking at graphically. What do we see? So we see that there is this function, and we can tell by our rules that this is top heavy. And so when it's top heavy, there are no horizontal asymptotes. We can also see that just graphically. There's no simple line that this function comes close to and then doesn't touch. The the vertical asymptote is 0, is x equals 0. It will never touch the y-axis. As graphically, we can see that. Horizontal asymptote symbolically, since the degree is higher, so top heavy, like P of X is greater than Q of X, we know that the horizontal asymptote is none. And then for vertical asymptotes, we just take that bottom value and say, hey, set it equal to 0. So x equals 0. That's going to be our vertical asymptote. Let's do it again. Visually, it looks like horizontally, this line right here of y equal 2, these functions come really close to it, kind of like an electric fence, but they will never touch it. Vertically, they come really close to this line of x equal 3 and x equal -3, but they don't touch it. So graphically, I can see horizontal asymptote at x equal 2. I'm sorry, y equal 2. Vertical asymptote at -3 and +3. But let's look at it symbolically. Looking at our function, they're the same value, so you take the coefficients. Therefore, y equals 2 over 1, or y equals 2. You say, is this in its simplest form? The answer is yes. There's no simplification that I could do. And so you take the denominator and you set it equal to 0. And you solve. X squared equals 9. Would which values make that true? 3 and -3. Doing another example. It looks as though it comes really close to this line, never touches it. So for horizontal asymptote, we have y equals 3/4 because this is 1. So that's 1/4, 2/4, 3/4. Vertical asymptote, we don't have any. I don't see any anywhere. Let's do this symbolically. Looking at it, we have the same degree. So we know we're going to take the coefficients 3/4. The function is in its lowest terms. The way we know that is because it's not factorable. 3x squared minus 5, I can't reduce that. 4x squared plus 9, I can't reduce that. So we take our denominator and we set it equal to 0. And so we solve, we subtract 9 and divide by 4. And we get x squared equals -9/4. Well, you know, you can never square a number and get a negative. So there are no real numbers that would make that true. So there's no vertical asymptote. Again, visually, for example, 9, we have horizontal asymptote right here at y equals 0. And a vertical asymptote at x equals 2. Symbolically, we're going to look for degree over degree. Well, this is bottom heavy. So therefore, we know it's y equals 0 for the horizontal asymptote. And then for the vertical asymptote, we take the denominator and we set it equal to 0. And we solve. You could write it in quadratic form. I'm sorry, factor form, or you could just use the quadratic formula and solve it. X cannot be 2 is the answer. All right, so we're going to do this again. We're not doing it visually. We're doing it symbolically, but you could totally graph this and do it visually if you wanted to. If you're doing your homework and you want to use Desmos, then Desmos is a great calculator for you to visually see the asymptotes. I see the degree being the same. So I take the leading coefficients, 3 and -2. The rational function is in its lowest terms because I cannot, like they don't have anything in common. So now I just take the denominator, I set it equal to 0, and I solve. So the vertical asymptote is x equal 1/2. Find the vertical or horizontal asymptotes. Horizontal, let's look at it. So this is bottom heavy because we got a 1 up here and a 2 down here. So we know our horizontal asymptote is 0. For the vertical asymptote, we see if everything is simplified, and it is. So we're going to take that bottom and we're going to set it equal to 0 and solve. Again, you could factor. Basically, in factoring, you're taking the 2 at the top and the 3 from the middle and saying what 2 numbers multiply to equal 2, but add to equal -3. That's -2 and -1. So that's how we get that. And then we solve. X cannot be 2 or X cannot be 1. Those are our vertical asymptotes. Okay. Another example here. My bad. I had to look at that and make sure I had it right. I don't know what I'm doing. Hold on just a second. There we go. All right, find a horizontal or vertical asymptote in number 12. So horizontal asymptote, we're gonna use that same chart. We have a 2 over a 1, and so it's top heavy. That means that the horizontal asymptote is none. For vertical asymptotes, we need to make sure that it's simplified first. So x squared minus 4 can be simplified. That's a difference of 2 squares, so it's just x plus 2 and x minus 2. And then you have x minus 2 in the denominator. So those two cancel each other out. So there is no vertical asymptote. Because there's no denominator. Well, the denominator is 1 rather. And when it's 1, that can never be 0. All right, example 13. Write a formula f of x for the rational function that satisfies the given condition. Vertical asymptote at x equal 1, no horizontal asymptote. So we're looking for something that has a vertical asymptote at x equal 1. A vertical asymptote means that the denominator, if I plugged in 1, it'd be 0. And then no horizontal asymptote, that means that it has to be top heavy. So I just take a value and make a make a numerator where the degree is higher. There we go. You could have anything at the top really, as long as the degree is higher. Vertical asymptote, I'm sorry, at x equals negative plus or minus 3. Horizontal asymptote at y equals negative 2. So in this case, I'm saying that my denominator, plus or minus 3 have to make it negative. So I'm gonna say x squared minus 9, because if I plug in 3, then I get 0. If I plug in negative 3, I get 0. But then on the horizontal asymptote, it's actually has to be negative 2. So that's gonna be my coefficient. And my degree has to be the same so that I actually have a horizontal asymptote. Okay, now we want something with no vertical asymptote and the horizontal asymptote at y equals 0. So remember, if it's bottom heavy, it'll be y equals 0. So as long as we have something that's bottom heavy. And for the no vertical asymptote, as long as it's like a function that if you were to plug in any value, it's still going to be a positive value. It's not going, it's not going to be 0, then that's fine. So remember, x squared plus 1 can never equal 0, because you can never have a value that's going to actually equal a negative number. So this is fine. It could have also been x squared plus 4 or x squared plus 9. It don't matter, because when you solve these, it's going to say x squared equals some negative number, and that we know that that would never be the case in the real number system. So then for the horizontal asymptote to equal 0, just put x, make it bottom heavy. So you can put x or you can put a whole number. Either way, it's less than, the degree is less than the denominator. Okay. And this is our last example before we get into the application problems, I believe. So solve a rational, how do you solve a rational equation? So you have this rational equation and it's equal to a whole number. There's a couple different ways to do this. So first off, find out the domain. And so in this case, the domain is -1/2. Because if you put a -1/2 in there, you get a -1 plus 1, which makes that 0. So our domain is that x cannot be -1/2. Okay. Once you solve this equation, you want to eliminate the fraction. So basically, you multiply both sides by the 2x plus 1. And when you do that, you get 3 equals -2x minus 1. So I'll show you in my handwriting. Maybe that'll help. Basically, you're going to multiply both sides by 2x plus 1. These cancel, and you're left with 3 equals -2x minus 1. And you solve that equation regularly. Another way to see this, and a lot of students like this actually a lot better, is to see these as equivalent fractions where you can cross multiply. So you write it like that as two fractions that are equivalent and you cross multiply. 3 times 1 is 3. -1 times 2x plus 1 is -2x minus 1. And it's the same situation, it's just seeing it differently. So do whichever one makes most sense to you. And then when you solve for x, you get that x equals -2. And that's fine because our restriction was that x couldn't be -1/2. Okay. And anytime you multiply by a variable, you do run the risk of like creating solutions, ones that don't work. So that means you just got to always check your work. So if you plug -2 in, then you'll see that -2 does give you a value because it is a part of our domain. The domain is just that x couldn't be -1/2. All right, this last example is an actual application example. So let's go through this and go through it kind of slow. Suppose that a construction zone can allow 50 cars per hour to pass through, and that the cars arrive randomly at the rate of X cars per hour. So construction zone can only allow 50 cars per hour to pass. And like they're arriving at random times. So you don't know when they're going to come, but you just know every hour you can only allow 50 cars. Then the average number of cars waiting in line is given by this rational equation. It says evaluate n of 40. That means put 40 in for x and interpret the results. So when we put 40 in for x, basically we get 3.2. Now we need to interpret that. 40, because it says x cars per hour. So 40 cars are coming randomly, like 40 cars per hour. And then this number is the number of cars waiting in line. So 3.2 cars are waiting in line at any given time. Sorry, let me go backwards so you can see that interpretation. About 3 cars are waiting in line at any given time if 40 cars are arriving randomly. Okay. So it says explain what happens to the length of the line as x approaches 50. Well, if you think about this in common sense, like the more cars that are arriving every hour means that like the slower the line is, like so more cars will basically be waiting. So as we approach 50, which is the max, then we know that more cars will be waiting. So because there's a vertical asymptote at x equals 50, the average number of cars waiting in line increases dramatically as we approach the 50. So like that's like the 50 car, people coming, but they just can only allow 50. So the more people come, as we approach the 50 number, the number 50 rather, then the line is longer and longer and longer. That's basically what it is saying. That is it for 4.6. Check me out tomorrow for 4.7.